Hello everyone. Today we are doing 2.1d, which is limits of piecewise functions. Let's say we have the function f of x equals 2 minus x when x is less than 0, negative x squared plus 2 for 0 is less than or equal to x is less than or equal to 1, and x plus 3 for x is greater than 1. If we want to graph this, which sometimes we will, let's draw our coordinate plane, and I'll, attempt and fail to draw straight lines as usual. I'll switch colors for the graph. So let's start with x is less than 0. So we have the line 2 minus x, which is just a line with a slope of -1 and a y-intercept of 2. So the y-intercept would be 2 right here. For now it's a hole because x is less than 0, so it's not included. And then we'll apply the slope, so up 1 to the left 1, up 1 to the left 1. It'll look something like this. Oops, sorry about that. Then we'll connect. We're really only worried about exact points where the function has its kind of connecting points for the different pieces of the piecewise function. Then we have negative x squared plus 2, which is an upside down parabola with a y-intercept of 2. So it starts here. You can fill in the hole because it will be included for the second function. And then for negative x squared plus 2, we're going to 1. So if we plug in 1, negative 1 squared plus 2 equals 1. So we'll have the point 1, 1. And these are both less than or equal to. So that's closed, and we'll just kind of curve it, and it'll look something like that. Now we have the line x plus 3 when x is greater than 1. So starting at 1, the point will be 1, 4, because 1 plus 3 is 4. So we have a point there, and then we have a slope of 1, up 1, over 1, up 1, over 1, so it'll curve that way. So our function will look like that, or pretty close. As far as what piecewise functions are used for in real life, one example is tax brackets. So depending on your income level, you're taxed differently. And also pricing when you buy in bulk. Maybe if you buy a certain amount, you pay a certain price for the first, 100 you buy, and then for the next 100 to 200, let's say you have another price, and over 200 you pay a different price. So a very vague example. So we find the limits of piecewise functions where the function changes definition. For example, up above for our first f of x up here that we drew the graph of, we would have checked at 0 and 1 because that's what shows up over here on the right. Okay, so let's look at another piecewise function. G of x equals negative x, where x is less than -2, 1/2 x squared minus 1, for -2 is less than or equal to x is less than 2, and negative x plus 3, where x is greater than 2. And we will evaluate limits at -2 and 2, which is where they connect or don't connect, depending on whether a limit exists, right? But basically we're looking at these 3 different functions that are part of the piecewise and where the definitions change. So first we'll look at the limit as x approaches -2 from the left of g of x. And from the left of -2 is anything less than -2. So we'll look at this top definition, negative x. So then the limit is going to be -2, which is 2. So essentially, for finding the limits this way, we're going to evaluate basically -2 at whatever definition we're looking at. So since we're looking at to the left of -2, less than -2, we use negative x there. When we look at the limit as x approaches -2 from the right of g of x, that's greater than -2, excuse me, so we'll use this middle definition. So 1/2 times -2 squared minus 1, which is 1/2 times 4, which is 2, minus 1 is 1. And 2 is not the same as 1, obviously. So the limit as x approaches -2 of g of x equals, well, it doesn't exist because they don't match. So if we were to graph this, which we don't need to, the function would not be connected at -2. Now we'll check 2. So the limit as x approaches 2 from the left of g of x, to the left of 2 is right, less than 2, but right next to it on the left, so we'll use 1/2 x squared minus 1. So 1/2 times 2 squared minus 1. 1/2 times 4 is 2, minus 1 is 1. The limit as x approaches 2 from the right of g of x is going to be greater than 2, but right next to it. So we'll use negative x plus 3. So -2 plus 3, which is 1. Since 1 is, the same as 1, we have a limit that exists. So the limit as x approaches 2 of g of x equals 1. Let's look at another one. F of x equals -x plus 3 for x is less than 2. 3 when x equals 2, and -x squared plus 6x minus 3 for x is greater than 2. Pause the video for a minute and try to find the limit of f of x as x approaches 2. Okay, I'm assuming you tried it. If not, that's cool too. So again, 2 is the only thing we have to check because over here on the right, all I see is a bunch of 2's, no other numbers. So if we look at the left, the limit as x approaches 2 from the left of f of x, the left is less than 2, so we're using -x plus 3. So we have -2 plus 3, which is 1. The limit as x approaches 2 from the right of f of x is going to be greater than 2, so we use -x squared plus 6x minus 3. So -2 squared plus 6 times 2 minus 3. So this is -4 plus 12 is 8, minus 3 is 5. Since those are not equal to each other, the limit as x approaches 2 of f of x does not exist. Keep in mind, since it's a limit, basically the fact that when x equals 2, f of x is 3 doesn't matter for limits because we're only looking at what it should be or what it's approaching from the left and right. But if we wanted to know what f of 2 was, we could say it was 3. But again, what the y value is makes no difference to us if all we're looking for is limits. Okay, now we have something a little bit different. Let's say we're given the limit as x approaches 1 of the absolute value of x over x plus 1. If we want to calculate this limit, or find this limit, we need to create a piecewise function. And the reason we need to do that is because this function behaves differently when x is greater than 0 than it does when it's less than 0. So now let's define this as h of x, arbitrary letter. We just haven't used h yet, so I'm going to use it. So our options, that absolute value of x can either be a positive x, and then we have x plus 1 in the denominator, or it can be a negative x divided by x plus 1. So two different functions. And the top one applies if x is greater than or equal to 0, because x is positive. And the bottom applies if x is less than 0, because x would be negative. So now, if we were just finding general limits here, we would look at 0. But our initial problem was up here, and our goal is to find the limit as x approaches 1. So let's look at the left and right. The limit as x approaches 1 from the left of h of x to the left is less than 0. So we'll use this bottom one. Just kidding. 1 from the left is not less than 0. This is good. Maybe you would have made this mistake too. I don't know. But so 1, actually, for both of these, we'll use this top equation, okay? Because to the left of 1, let's say it's like 0.9, that's still greater than or equal to 0. So we'll use the function x over x plus 1. So we'll get 1 over 1 plus 1, which is 1/2. And the limit as x approaches 1 from the right of h of x, let's say we're looking at like 1.1, so pretty close, it's still greater than or equal to 0, so we use the same function again. So 1 over 1 plus 1, which is 1/2. Since those are the same, the limit as x approaches 1 of h of x is 1/2.